Offshore oil and gas engineering operates in an environment with zero margin for error. When you are processing volatile fluids hundreds of miles from shore, mechanical failure is simply not an option. To understand the engineering required to secure these facilities, we are deconstructing the safety architecture of a specific gas processing unit. This system operates at 80 bar of pressure, with extreme temperature swings, ranging from -10 degrees Celsius to 350 degrees. This data maps environmental hazards in the Andaman Sea. Node 1 shows the system handles sour gas with 5% hydrogen sulfide, a highly toxic compound. Node 2 highlights the external threat, constant 30-degree warm seawater exposure, which drastically accelerates equipment corrosion. To survive these conditions, engineers must solve a three-part material equation. In this exploded diagram, we see the pressure-containing body, the internal trim, and the seating elements. Each component must be independently matched to the specific process fluid. Valve selection in this environment represents the boundary between stable operation and systemic failure. Every mechanical specification must be physically capable of containing the process fluid. Misapplication at any node guarantees a breach of the pressure boundary. Every valve serves one of four non-interchangeable functions. This grid shows valves designed strictly for full isolation, flow throttling, backflow prevention, or overpressure relief. Crossing these boundaries causes mechanical destruction. Using an isolation valve to throttle high-pressure gas rapidly erodes the internal mechanisms. We are now going to reverse engineer the mechanical topology for 5 critical nodes within our offshore sour gas system. Our objective is to translate abstract fluid dynamic requirements, like flow rate, pressure drop, and chemical composition, into the exact mechanical architectures built to withstand industrial punishment. Node 1 is the 12-inch main high-pressure inlet line. The engineering requirements here are explicit. We need fully unrestricted fluid flow, positive manual isolation for vessel maintenance, and a completely clear path to run pipeline cleaning devices, known as PIGs. The optimal architecture is the slab gate valve. When open, the gate retracts entirely, creating a straight-through bore with zero flow resistance. But this dictates a strict constraint. It has only 2 functional positions, fully open or fully closed. It cannot throttle flow. If left partially open, high-velocity fluid violently erodes the metal seat and vibrates the disc against the valve body, destroying the seal within days. Beyond mechanics, this node has a strict environmental constraint. Because the inlet handles sour gas, the carbon steel valve body must strictly comply with the NACE MR0175 metallurgical standard. If the metal's hardness exceeds HRC22, hydrogen atoms infiltrate the metal lattice. This causes sulfide stress cracking, triggering a sudden, explosive brittle failure under normal operating pressure. Moving to Node 2, the 4-inch chemical injection line, the mechanical requirement shifts. We no longer need full-bore flow. Instead, we need precise, proportional regulation of the injected corrosion inhibitor. The solution is a needle-type globe valve. A tapered plug is driven into the seat interface, allowing minute, proportional changes to fluid volume. But this precision forces the fluid through a tortuous S-shaped path. Forcing high-pressure liquid to change direction twice inside the valve body generates a significant pressure drop. This friction consumes pump energy, making globe valves inefficient for simple isolation. Because the corrosion inhibitor itself is highly corrosive, the metallurgical equation must be updated. We specify a CF8M stainless steel body with trim 12 internal components to survive direct fluid contact. Note 3 is the 8-inch emergency shutdown valve, or ESDV, located on the unit's outlet. If a disaster occurs, the safety system must automatically fail closed in under 5 seconds to isolate the facility. Multi-turn gate and globe valves are too slow for this task. Rapid isolation requires the selection of a quarter-turn ball valve. This rotation diagram illustrates the simplicity of the mechanism. A metallic sphere features a central bore providing zero pressure drop. With a quick 90-degree rotation, the solid side of the ball completely halts the process flow. Because this valve controls bulk hydrocarbons, it requires an API 607 fire-safe certification. This proves the internal seal will not melt or fail, even if engulfed in a 750 degrees Celsius fire for 30 minutes. At Node 4, the discharge line of the reciprocating compressor, the system must autonomously prevent reverse flow if the pump suddenly trips offline. This requires a check valve, which opens and closes automatically based on fluid pressure, but reaction speeds vary. A traditional swing check takes over a full second to close, while a dual-plate wafer check snaps shut in just 1/10 of a second. That fraction of a second dictates whether a system survives. If a slow closing valve allows fluid to reverse momentum before slamming into the closed disc, it triggers water hammer, a destructive pressure shockwave traveling backward through the pipe. To prevent this shockwave from shattering the compressor housing, specifying the fast closure of the dual-plate check valve is the only reliable solution. Our final node is the ultimate safety mechanism, protecting the high-pressure separator vessel. This equipment has a maximum allowable working pressure of 85 bar. We protect it with a pressure relief valve. This balance graphic shows it's a safety barrier, not a control valve. It sits dormant until process pressure physically overcomes the spring force, instantly venting the system to prevent an explosion. Hydrocarbon gas cannot be vented locally. As shown here, the gas is routed through a network of headers to the facility's flare stack, where it is burned off at a safe distance from platform personnel. A PRV opening indicates a critical system state. Its activation proves that every other sensor, control valve, and automated safety system has already failed. This matrix summarizes our engineered architecture: gate for isolation, globe for control, ball for shutdown, check for backflow, and PRV for relief. Beyond type, engineers must legally bind manufacturers to a specific leakage tolerance, an API 598 shutoff class, like Class 6 for zero leakage. Matching mechanical motion, pressure drop, and metallurgy to the process fluid completes the theoretical design. Before this hardware reaches an offshore platform, the theoretical design must be proven through physical testing. This infographic outlines the API 598 factory test protocol. In Step 1's hydrostatic shell test, the body is pressurized to 1.5 times its rating for a sustained duration. If the inspector sees a single drop weeping through the casting, it is rejected. After the shell is proven sound, the valve undergoes a low-pressure seat test, verifying that the internal seals meet the exact leakage class specified on the original engineering datasheet. Mastering this functional taxonomy allows engineers to build high-pressure systems that protect human life, serving silently for decades in Earth's most unforgiving environments.